Technology. He is well known for his work on the theory and mathematical modeling of internet congestion control algorithms and optimization in power systems. Professor Lowe received his bachelor degree in electrical engineering from Cornell University in 1987, PhD in electrical engineering from the University of California, Berkeley in 1992. He was then with Bell Labs from 1992 to 1996. Melbourne University of Australia subsequently from 1996 to the year 2000, and then he joined Caltech in 2000, beginning of 2000. He was co-founder and CEO of a startup called FastSoft from 2006 2008, and the chairman of the startup from 2006 to 2012. Upon returning to Caltech after FastSoft, his research began to focus on the control and optimization of distributed energy resources for future smart grids. Professor Lowe is an IEEE Fellow, a co-recipient of an R&D 100 Award, and he has also received numerous IEEE prize paper awards. He has been a chair or honorary guest or adjunct professor with Zhejiang University in China, National Taipei University of Technology, Shanghai University, and Swinburne University of Technology in Australia. Professor Lowe, it is truly a great pleasure to have you here as a speaker today. And without further delaying your talk, I would like to hand the floor to you.
Thank you very much, Ryan. Thank you very much for the invitation, also the long introduction. So I'll talk about OPF for distribution systems, 2 sessions. Oops, okay, so, okay. So the first session, probably around 55 minutes, I'll talk about OPF, both for the single phase, which you should think of as a balanced 3-phase operation, and therefore we are looking at a per phase equivalent circuit, and also for 3-phase unbalanced operation. And I'll talk about semi-definite relaxations, some properties and conditions for exact relaxations. And then we'll take a 10-minute break, and then I'll talk about OPF in a different model, branch flow model that was originally designed specifically for distribution systems that has radial structure. So I'll talk about OPF and semi-definite relaxations, single phase and extension to 3-phase, and also some properties about the semi-definite relaxations. And hopefully we'll have time. I'll talk about an interesting property where it's known that OPF is non-convex and also NP hard. So it's hard in theory. In practice, however, it seems to be easy in the sense that if you run semi-definite relaxations, very often you get exact global optimal solution. Or if you just run local algorithm, you probably get a global optimal solution. So I will talk about some of the empirical experiences and also proof conditions that are either necessary or sufficient for a non-convex problem to have both exact relaxation and also no spurious local optimal. So let's get started. I guess by now everyone knows why we're interested in power systems and some of the applications in power systems, some of the computational issues in power system. So I skip all those motivations, introductions, and just jump right into optimal power flow problems and convex relaxations. There's a very nice recent survey by Dan Mosen and Jan Hiskins that contains a lot more details. Okay, so bus injection model, the first session. OPF in a single phase and then the three-phase extension. So just to fix the notations that we are all on the same page on what the model is. A network, so it's cut off a little bit on the top. Okay, I'm not sure what I can do about that, so hopefully it's okay. The title for the slide, just not too important, is power flow model. So a model of a network is simply a graph with N, that is a set of buses or nodes, E, which is a set of links or transmission lines. So for each bus J in the set N, there are two variables, the real and reactive injections Si or Xj should be, and therefore Sj is a complex number, or you can think of it as a pair of two real numbers. The second voltage associated with each bus J is a complex voltage phasor Vj. Or you can think of as either real and imaginary part of the voltage, or in polar form, there will be the magnitude and the angle. For each line Jk in the set E, each line is characterized by three complex numbers. Yjk of S is the series admittance. Yjkm and Ykjm, all complex numbers, are charging admittances for the line Jk at either end of the line. So pictorially, you have this representation. So each node J has two variables, Sj and Vj. You can also have an Ij, which you can express in terms of the other two variables. So we'll focus on mostly the injections Sj and voltage phasor Vj. And then the line is characterized by those three numbers. And you can think of a line in our model can be a model of a transmission line with this pi equivalent circuit, or it may not be a transmission line. It could be say a transformer, but also it has a pi equivalent circuit, and therefore generically we'll call this a line, even though it could be a model of different physical components. So a power flow equation that defines the model, the power flow model, can take different forms, and this is a complex form. You can also have polar forms and Cartesian forms and so on. So here in the complex form, Sj, which is the complex power injection from node J to the rest of the network, is related to the voltages at node J and also at its neighbors in this particular manner. So Sjks again is a series admittance on line Jk that is connected to J. Yjkm is a charging admittance at the endpoint J of the line Jk, right? And Vj is the magnitude, and Vk is the voltage phasor, the product of the voltage phasor. The H is complex conjugate, right? So it's the Hermitian transpose if it is a matrix later on, as we will see. So that's the basic model. You have a power flow equation that defines how injections in the network are related to the voltages in the network. And OPF is simply a constraint optimization. And the reason it is so important is because it underlies numerous power system applications. And therefore, abstractly, is simply you want to minimize some costs as a function of the variables, the vector of injections S, the vector of complex voltage phasors V, subject to two kinds of constraints, equality constraint and inequality constraint. So the equality constraint will be power flow equations for us. In practice, there may be other equality constraints, but for us, the simplest form of OPF that we'll consider, the equality constraints will just be the power flow equations we saw earlier. The inequality constraints represent operational constraints. For example, if S represents we want to schedule generations, then there will be injection limits. So Sj, which is a complex number that represents the real and reactive power of, say, a generator, for example. So we're going to write this. Sj lies between some lower bound and upper bound. And here it means if you look at this is really a shorthand for two inequalities, both with real quantities on a real part and an imaginary part, for example. You will include voltage limits. The voltage magnitude needs to lie between, say, 5% of nominal and line limits. Line limits can be represented in terms of the line currents, magnitude squared, or the apparent power, for example. So more concretely, the power flow equations that we would mostly use is this complex form that we saw before. Operational constraints will be injection limits. So again, it's a really a shorthand for two inequalities, voltage limits and line limits. Right? So here, there is a line limit for sending end current from J to K, and also the sending end current from K to J. So they may not be necessarily be minors of each other when there are charging admittances. Okay, so that's the mathematically, that's the problem. You have some cost. Cost can represent generation cost, can represent real power loss over the network, for example. Or in demand response, it could be some kind of a user disutility when they reduce their flexible loads, for example, flexible demands. So you have a certain objective cost function that you want to minimize that depends on your application, subject to these two sets of constraints, the powerful equations and operational constraints, and that's OPF. So the first thing we'll do is we'll write this problem as a quadratically constrained quadratic program, QCQP. Right? So the trick to do that is quite simple. If you look at this, then this is on the right-hand side looks quadratic, right, in voltages. So if you look at the power injection from node J to the rest of the network is the voltage, complex voltage phasor at node J multiplied by the complex conjugate of the current injection. So Vj, which is a complex scalar, you can write in terms of the voltage vector, right? So Ej is the N is the number of buses in the network, then Ej is an n-dimensional vector with a single one in the j's position and zero everywhere else. Right? So this is the transpose of Ej. So the product will pick up Vj, and similarly, this is Ij complex conjugate. So you use I equals YV, substitute into this, you get this equation, but this is just a complex scalar, and therefore E equals the trace. Now you use the property of the trace that you can swap the order of the arguments. You move this basically to the other side successively. You get this. You get to this form where there is a matrix that depends on J, and then there's this quadratic form, right? And therefore, we write the power injection as a quadratic form in the voltage vector. And therefore, the powerful equation will take this form, which is quadratic. Now, Yj that depends on the admittance matrix Y, one for each bus J, is not Hermitian, and therefore this quantity is typically complex. But we can look at the Hermitian component and school Hermitian component, and then write the real part of each injection, that is the real part of this quantity, in terms of a Hermitian, in terms of the Hermitian matrix phi j, and also the Hermitian matrix psi j. And therefore, for each node j, we can represent the real part of the power injection as a quadratic form that involves a Hermitian matrix. And therefore, this quantity, each of these quantity, is a real number. And therefore, if we look at the constraints before, okay, here, if we look at the constraints before, Sj, we can write this will be the real part of Sj greater or equal to the real, let's say P under bar J, P upper bar J, and then the imaginary part of Sj is Qj bar. But this is simply a quadratic function in the voltage vector V. Right? Similarly, well, this is quadratic function in the voltage vector V, the voltage limit. And here you can write the current, the sending end current, as a function of V. And the magnitude square will give you a quadratic function of V. And the bottom line of all this manipulation is that you can write OPF as a quadratic constraint, quadratic program that takes this form. So assuming the cost that we're interested in minimizing is also quadratic, take this quadratic form. And typically for most applications, the matrix C0 is nice. Let's say positive definite or positive semi-definite, for example. And therefore the objective function is convex, is quadratic convex. The constraints all take this form. So this is the injection limit, this is the voltage limit, and this is the line limit. They are all quadratic functions of V. The matrices involved are Hermitian, but they are not positive semi-definite. And that's why it's a non-convex problem. So it's a non-convex QCQP, and that's the problem. So that's the single phase. In distribution systems that we're interested in, however, have two important properties. One is that most distribution systems, with few exceptions, have radial structure. That is, the graph structure is a tree. Secondly, is three-phase but unbalanced. And therefore, we cannot really look at a per-phase equivalent model, but really have to look at the three-phase model. So in general, a network consists of components that look something like this. You have a three-phase source, either in Y or delta configuration. You have three-phase loads, and they're connected by three-phase lines. And therefore, we have to develop models for each component, the three-phase source, the load, and also the transmission lines. So we're going to do that. And at the end, what we'll get is a single-phase equivalent of this three-phase circuit. So that's what we're going to do. So once we get the single-phase equivalent, then we can formulate OPF in the three-phase model and get a single-phase equivalent OPF, which will also can also be written as a non-convex QCQP, just like the one we saw in the previous slide. And therefore, the conclusion is going to be whether we are dealing with single-phase system or unbalanced three-phase system, we can write OPF as a QCQP. And therefore, later on, we're going to look at how do we develop semi-definite realizations of general QCQP, and also what are the conditions for exact realization. Okay. All right, so let's fill in the details. So we have this three-phase source connected to three-phase load by three-phase lines, and those sources and loads may have neutral lines if they are in Y configuration, for example, which may also be grounded on either or both ends. So the impedance load, if it is in Y configuration, and this is one typical component where you have three-phase, four-wire impedance load. So the four wires consist of the wire for phase A, which is this, phase B, and phase C. And then you have a neutral line that is grounded. So these are the four wires. And therefore you can connect, for example, a three-phase line through with this four wires. So depending on how you do the connection, the voltage, let's say VA, right, VB and VC, can be a phase to neutral voltage, line to neutral voltage, or it can be a line to ground voltage, depending on how you connect. right? So here's an example where the voltage that we're looking at, the voltage at each node, right, each bus, three-phase bus, consists of three components, VAG, VBG, and VCG, which are aligned to ground voltage drops. Right? So in that case, you can look at the circuit, you can write down the Kirchhoff laws, and you get the equivalent three-phase impedance that relates the terminal voltage and the terminal current. Right? So the currents also will be a three-dimensional vector. These are the line currents, IA, IB, and IC. So the linear relationship between the phase voltages and the line currents is defined by this Z of Y. That is the equivalent impedance for the three-phase impedance low in Y configuration. So they consist of the impedances of individual in individual phases. So ZA, ZB, and ZC. Right? So these are the actual impedance in each phase. They may not be the same, therefore it's unbalanced. And also there can be an impedance that connects the ground to the neutral. Right? And these component impedances make up the equivalent impedance that relates terminal voltages and currents. So that's the case if you have Y configuration. If you have a delta configuration, there's no neutral. Again, you can look at the circuit, you can write on the KKT. So, and the basic relationship is across the each impedance, say ZA, for example, there is a voltage drop across the impedance, that's the low voltage. There's a current through the load, that's the current feeding the load, which is IAB, right, between these two phases. But given this IAB and VAB and the other two phases, we want to write the terminal voltages VA, VB, and VC in terms of the line currents IA, IB, and IC. Again, you can do your circuit analysis, and then you will get this equivalent impedance Z of delta, right? That relates to terminal voltages and the line currents. And therefore, if we have a circuit with three-phase loads, for example, in Y and also delta configuration, then we can convert. One way to do the analysis, the circuit analysis, is to convert all delta loads to equivalent Y loads. Then you can do the circuit analysis consisting of all three-phase devices all in Y equivalent Y configurations, just like in the balanced case, except that this is unbalanced three-phase, and therefore you cannot have a per-phase equivalent, but you just carry out these entire three-phase equations, and you can do the analysis. So once you get the VA and IA, those phase voltages and line currents, then you can obtain the low voltages and currents. So that's good. When you are trying to do optimal power flow, on the other hand, then depending on your applications, what you can actually optimize or actually control may not be the line currents and terminal voltages, but rather maybe the low currents. And you may be interested in the low voltages stay within a certain bound, for example. And therefore, your OPF formulation will involve VAB and IAB star, for example. That will be the low power. Think of the case where you want to do demand response. Then you want to optimize over the low power, for example. Right? Then you could have this relationship between the low voltages and low currents and the terminal voltages and terminal line currents, which will be related to the powerful equations like we saw before. Right? And that can create some computational issues. We won't have time to go into that, but just be aware of that. But at least in theory, you can write everything down. You can formulate your problem. So those are the components. You have three-phase loads or generators in Y or delta configuration. Then we have a model for three-phase lines. Now, the equation that relates the line current over line JK. So IJK is the sending end current from bus J to bus K. That is related to the voltage at J and also bus K. Similarly, this is the current, sending end current from K to J, right? And again, it's parameterized by three parameters. Now for single phase, those three line parameters and also the currents and voltages are all complex scalars. In three phase, they become complex 3x3 matrices, all of them. So if you have a three-phase, four-line device, you could have a three-phase lines plus a neutral line, and therefore your three-phase line consists of four conductors. You can write down your equations relating the currents and the voltages that involve 4x4 matrices. If you assume either the currents on the neutral is zero or the voltage is the same across the line, then you can do Coulomb reduction. You get to 3x3, involving only the phase currents and phase voltages. And therefore, this when I say this, all these are 3x3 matrices, you assume that process has been done. So you do all that, and then you get a equivalent matrix that describes the relationship between the three phases, right? And therefore, the equation look formally the same, except that all quantities becomes the line parameters become 3x3 matrices. The variables, the currents, say IJK or IKJ, or the voltages are three-dimensional vectors. Okay, so that's how we can model a three-phase line. Then we can put everything together and then write down powerful equations using a admittance matrix. So this is the admittance matrix. If you write this down and then you conclude that they look exactly the same as in the single-phase case, except that each entry of your admittance matrix is no longer a complex scalar, but rather a 3x3 matrix, like the 3x3 matrix that we talked about before in the previous slide. So here's an example where we have three buses, 1, 2, 3, two lines, each characterized by, so in this case, assuming there's no charging admittances, then this is the series admittance, phase admittance matrix. So Y13 connecting bus 1 to bus 3 and Y23. The overall admittance matrix, which will be 3 times n by 3 times n, where n in this case are 3, corresponding to 3 buses. So this 3 corresponds to phases ABC. Right? We'll take this form. So just like in a single phase, this will be minus the series admittance between bus 1 and 3, because 1 and 3 is connected, and this is the diagonal term, which will be just the plus of Y13. So here is the connection Y13 and Y23, and this is the diagonal entry. So again, for three-phase system, each entry yjk is now a 3 by 3 matrix. And therefore, if you expand this, it looks something like this. Right? The structure is just like a single phase, except now you have the matrix matrix Y overall is 3n by 3n complex matrix. But it's still this 3n by 3n matrix is a complex symmetric matrix. It's not complex summation. That's the problem, but it is complex symmetric, just like in a single phase case. Okay, and therefore, there is a single phase equivalent where you can think of, so this is a bus with three phases, phase A, B, and C. So this is bus J, and this is bus K. At each bus, there are three variables, voltages VA, VB, VC. It can also be three injections, SA, SB, and SC on at each end, for example. So each bus, you can think of this as a node or bus in a single phase equivalent. And the graph will be a click. So the voltage and currents in phase A depends on voltages. So the currents in phase A depends not only on the voltage drop between the two ends of phase A, but also depends on the voltage drop in phases B and C. And those parameters, these admittance or impedance parameters in that 3 by 3 matrix gives you the ratio of the voltage drop in a certain phase, say A, to the currents in phase B, for example. Right? So that's the cross off-diagonal terms. But you could think of, again, each bus in the single phase equivalent as indexed by the bus number and the phase. Right? So bus JA, JB, and JC, and so on. Now, if you look at this, then you can write down the powerful equations like we had before. So you have this, each equivalent bus is indexed by J, and the phase phi, which can be A or B or C, is related to the voltage at that single phase equivalent bus, J phi, and also the complex conjugate of the current injection from that bus to the rest of the network. Right? And then you play the same trick, you will get to this quadratic form. Right? So Sj phi is a quadratic form in VVH, right? Where this matrix that depends on J is given by this expression where Y is this 3n by 3n matrix, and Ej phi is a vector with a single one in the J phi location and zero everywhere else. Okay, so just like in a single phase case. So that's a single phase equivalent. And therefore, if you do all this, the conclusion is that in a three-phase system, you can also write your OPF problem as a non-convex QC/QP. So how am I doing on time? Oh, okay, good. All right, good. So that's the OPF as QC/QP. Now, OPF, as I mentioned earlier, is non-convex, and this is a really nice graph that some of you might have seen from Ian Hiskins. So this is just simple 3-bus network in a mesh, and you write down the OPF, you look at the feasible set, you get this beautiful shape or ugly shape. So it's non-convex and computationally difficult. So this is without other sources in non-convexity, such as you could have discrete variables, say in unit commitment problems, for example. Okay. So let's look at the semi-definite realizations. So the idea is very simple. Many of you may have seen some of these basic ideas. But since we have a diverse audience, let me just go through this quickly. So this is the problem we have, OPF. Here, it retains the same structure as before, except that I skipped the line limit, right, just to make the slide simpler. But the point is, you have a quadratic form, both in the objective function and also in the constraints. Again, the problem is Yj is not positive semi-definite. That's why it's non-convex. So we're going to characterize this feasible set in 3 different ways to characterize them, and each will suggest a certain convex semi-definite relaxation. Right? Now, notice that I have eliminated Sj as an optimization variable. Right? Again, you can write Sj as a quadratic form in voltage vector V, and therefore you can write everything in terms of the voltage vector V. And therefore the entire OPF, the entire minimization, will involve only the voltages as your optimization variables. So that's what this form is. Okay, so we'll look at how do we characterize the feasible set, the set of V's that will satisfy this set of quadratic constraints. And what are the different relaxations and the relationship among them? And when will the relaxation be exact? So that's what we want to understand. So let's look at a feasible set, which is this. And everywhere V appears, it appears as quadratic form. So it appears as VVH, right? So V is a column vector, VH is complex conjugate and transpose. So it's a row vector. And therefore you can think of VVH, which is a matrix, as your variable. And therefore this problem is equivalent to this. Right? So you replace VVH by a new variable W, which is n by n matrix. And you get this constraint, but not any n by n matrix. It has to be positive semi-definite and also of rank 1. So these 2 problems are equivalent in the sense that given a V that is feasible in the original problem or optimal in the original problem, there is a W that is feasible or optimal in the equivalent problem. Conversely, given a W that is feasible or optimal in the equivalent problem, there is a unique voltage vector V, unique up to a rotation, that is feasible or optimal for the original OPF. So in that sense, it's the equivalent. Now, notice though, that the original problem is quadratic in V. That's the problem. But in the new equivalent, new formulation, this lifted problem is linear in W. Here is convex in W in the PSD requirement, and is non-convex. The RAM constraint is the only non-convex constraint. So this is where the non-convexity is the RAM constraint, and therefore the relaxation is simply ignoring these constraints. So if you ignore the RAM constraint, you get a convex problem. You expand the feasible set, you get a convex problem. Okay, so this is basically just visualize what we just said. The set of feasible set is V that satisfies a certain set of quadratic constraints. The equivalent set W is the set of W's that satisfy certain linear constraints. That's PSD and RAM1, right? And the idea is that you have this RAM1 decomposition, right? So that's the idea. And again, relaxation simply expand the feasible set of W by ignoring the RAM1 constraint. That's the relaxation. So that's nice. You from a non-convex problem, now you get a convex problem, or at least a proximal problem, relaxation that you can solve. In theory, is simpler, is at least polynomial. practical scalability issues, let's ignore that for now, but that's very important when you actually try to compute something in practice. But ignoring that aspect, then you get a simpler problem, which is polynomial. The price to pay is that instead of n variables, now you have n square variables, right? One for each entry in the matrix W. Only order of n squared is a symmetric Hermitian, therefore is n times n minus 1 over 2. Okay, but still, on the order of n squared, that's a lot, right? So here's one example. You have 5 nodes, a graph with 5 nodes. The full matrix W will have 25 entries, right? Each being a complex number. So that's not very scalable. And therefore, let's take a closer look at the feasible set, right? So this is the feasible set V. And what we notice is that this expression is consists of, so assuming there's in this expression, we assume the charging admittances are 0, and this is the series admittance, right? So this expression, which is really your injection Sj, will involve voltages J and K only if J and K is an edge. So if J and K are not connected, then this expression will not involve Vj, Vk, H. Right? And therefore, the idea is that perhaps the off-diagonal entries, because the off-diagonal entries of W correspond to this Vj, Vk complex conjugate H. Right? And therefore, the idea is that perhaps the off-diagonal entries of W that do not correspond to lines in the graph are not important. So that's the conjecture, that's the idea. And therefore, maybe we can simplify our problem by trying to compute only the off-diagonal entries of W corresponding to edges in the graph. That's the thought, okay? So this is the diagonal entries, Wjj, and this is the off-diagonal entries, right? Okay, so, and therefore, if we can do that, then instead of n squared variables that we have to compute, we only need to compute n plus 2m or n plus m variables. M is the number of lines. Now, for real networks are very sparse, meaning that if you have n nodes, then instead of typically n squared lines, which corresponds to a fully connected graph, you typically have 1.5n number of lines. So it's linear in n, and not and even the coefficient is not that great, right? Typically, instead of n squared. Now, for a large network, the difference is huge, right? And therefore, the Kirchhoff laws, which corresponds to which really underlies these expressions, really depends linearly, or depends directly only on this Wg. Now, what is Wg? Wg is called a partial matrix. It is simply a set of complex numbers. That's all it is. A partial matrix is a set of complex numbers. But we can interpret this set of complex numbers as a n by n matrix where we only fill in or only specify a certain entry, but not all. Only the diagonal entries and off-diagonal entries, Wg of jk and Wg of kj, they correspond to lines in the graph, right? So if jk is not connected in the graph, then we don't specify its entry, right? So we're going to require the partial matrix to be Hermitian, meaning that the WGJK is complex conjugate of WG of KJ, right? So if we have this, then we say a partial matrix is Hermitian. And we're also going to define a partial matrix being positive semi-definite or a partial matrix being rank 1, right? Okay, so Kirchhoff law depends only on the partial matrix. It doesn't depend on the full matrix. Okay, so here's an example. If we solve semi-definite SDP, then we need to solve for n squared variables. Ideally, we want to solve only for the partial matrix WG defined by the graph G, right? So given the graph, it defines the partial matrix, right? With off-diagonal entries corresponding only to the lines in the network, right? So this line 1, 3, and so on. Now, okay, so that's what we saw before. Here's an OPF, the feasible set of OPF. Here's the SDP with positive semi-definite matrix, full matrix W and rank 1, right? So it depends on all entries. So the first idea is to maybe we can compute only the partial matrices defined by the graph G, right? So this is Kirchhoff law and also the voltage constraint, which depends only on WG. And we require the partial matrix to be PSD and rank 1. Now, first of all, what does it mean for a partial matrix to be PSD and to be rank 1? It means that if you look at the partial matrix for every fully specified submatrix, that corresponds to a click in a graph. That fully specified submatrix should be PSD. So every fully specified submatrix, which means that the n submatrix corresponding to every click, and you can look at only the maximum click, that's sufficient. So if every maximal click has a corresponding submatrix fully specified, that is PSD, then we say the partial matrix itself is PSD. Similarly for rank 1, right? And therefore we require the partial matrix to be PSD and rank 1. So that's the idea. And therefore now, instead of solving for the entire matrix W, can we solve only for a much smaller partial matrix? Well, this will be fine if G is chordal, meaning that it's either a tree that contains no cycle, or every minimal cycle is of length 3, right? It's a triangle. So if your graph has this property, then this idea will be fine. Then indeed you can just solve for sort of the smallest partial matrix defined by the graph G, WG, okay, which will be much, much smaller. Otherwise, if the graph is not equivalent, then this idea doesn't quite work. So the situation is explained in this property. So suppose we look at a full matrix W, and we look at a partial matrix WG defined by the graph that we saw before. And we look at a bigger partial matrix. So what it is that you take a graph, which if it is not a chordal graph, you can always get a chordal extension of the graph. The chordal extensions of any graph, they always exist, it may not be unique. So in particular, if given a graph, I connect every pair of nodes, then I just get a fully connected graph. That's a chordal extension, right? It's a very big chordal extension. So typically for practical network, large networks, it's very sparse. You can add some lines and get a chordal extension. And the idea is that you want to add lines so that the chordal extension is small. But it's kind of tricky. There's some subtlety involved in creating a good chordal extension for the purpose of this relaxation. Okay. In fact, the optimal quarter extension, optimal in some sense for your semi-definite relaxation, is NP-hard. But in any case, given a graph G, you find a quarter extension which is C of G. This quarter extension, which is a graph, defines a partial matrix W. So this WC of G is a partial matrix between the full matrix W and the sort of smallest partial matrix WG that's defined by the graph G, right? So fix a quarter extension, then you have three matrices, right, that we want to compare. And this is decreasing number of variables going down, okay? So let's compare three conditions, one on each matrix. C1 is that the full matrix is PSD in rank 1, we saw before. C2 is that you look at the partial matrix defined by a quarter extension of your graph G, right? You require that partial matrix to a PSD and rank 1. And the third condition is that if you look at every link JK, you look at the 2 by 2 matrix, right? So this is a very small matrix, just 2 by 2, one for each link. Require this 2 by 2 matrix to be PSD and rank 1. So these are just quadratic conditions for every line, okay? And then there's this cycle condition that we may come back to. And what it is that the intuition is that if you think of WG of JK, or the angle of that, as the phase angle difference across the line JK, then this condition says that if you sum the phase angle difference around every cycle C, they should sum to 0, mod 2 pi, right? So naturally, but this is the intuition underlying this condition, but it's a sort of nasty non-convex condition that depends on the angle of this complex number. But so there are three conditions.
May I ask a question?
Yes.
So from condition 2 to condition 3, are they equivalent?
Okay, great. Next slide. So okay. All three are equivalent. Okay.
Yeah, because condition 2 is caudal structure and condition 3 is a scale diagonal dominant structure with some extra constraints. So I don't know whether. Okay, thank you.
Yeah, great, good, very good. Okay, I should speed up. So this is an example. Let me skip the example since I run out of time. But this just try to explain what C1, C2 means. In the example, you can visualize what it means. Okay, but let me skip that. So what C1, C equals C2 mean, what C1 equals C3 means, and so on. Okay, let me skip all of that. So given any WG, which is the smallest partial matrix that satisfies C3, right? There turns out to be unique completion of W. You can fill in the unspecified entries that satisfy C1 uniquely. Okay, so there's some properties. Examples. Let me skip the examples. Okay, and therefore all these sets are equivalent. Okay. All right. So, okay, cycle condition. Okay, and therefore, because C1, C2, C3 are equivalent, it means that if you look at the feasible set defined by your original OPF, defined by SDP, defined by this caudal graph, and also the smallest the graph. Oops. Okay, so let me let me use a couple more minutes. Okay, sorry. WG, right? All these feasible sets are equivalent, and therefore, and there's some uniqueness too. And therefore, you can define your OPF just in terms of in this lifter space, and then just do your optimization. But of course, all of these are non-convex. But we know where the convexity, non-convexity comes, right? So if you ignore the non-convex constraints, then you get a convexization. And this is SOCP because the constraints here are just quadratic, right? It's a second order. Okay, then, so the relationship among them looks like this. So if you have a radial graph, then the now when you have a relaxation, right, SDP relaxation, the feasible set in some sense contains the feasible set of W. Now they're in two different spaces. One's in lifted space, but you can define precisely what you mean by that. Intuitively, you expand the feasible set. That's where you get relaxation. You expand the feasible set to be a superset that is convex. That's the intuition, right? Now here, they're all equivalent. If the graph is radial, if the graph is non-radial, then PSD and quarter relaxation has the same, the feasible set. There's one correspondence between the feasible set, and therefore they're equivalent in terms of tightness. But SOCP is strictly coarser, less tight. Okay, and therefore for radial network, always solve as SOCP because it's tight, is same tightness as even the SDP. For a mesh network, then those solve SDP, you should solve quarter extension, quarter relaxation. Okay, so okay, I will finish after this slide. So this is what happened. The feasible set of your SDP is this black curve, which clearly is non-convex. If you do SDP relaxation, then you optimize your cost over the purple region, which is a complex shape. It's convex shape that contains the black curve, and therefore it's a convex relaxation. SOCP is a yellow region that contains the purple region. So it's coarser. Right? This is a mesh network. Now, if you blow up this region, for example, then you can see that it turns out the boundary of your purple region is exactly the black curve. And therefore, if your cost function is something like this, for example, right, then this is the optimal point of your relaxation when you minimize over the purple region. Then your optimal solution will lie on the black curve. And therefore, it's feasible for the original problem. That's why in this case, your SDP relaxation is exact. And therefore, if you do a quarter relaxation, it will be exact as well. But if you blow up this region, you will see that the yellow region strictly contains the black curve. And therefore, if you do SOCP relaxation, you're going to get an optimal solution that does not lie on your black curve. That's why SOCP relaxation for this mesh network is not exact. Right? So this is the case for real power, for reactive power, the same story. I think I have to stop now. So this is just summary. Okay. All right. Yeah, there's just a few simulations to show that indeed SOCP is much more scalable, orders of magnitude more scalable than SDP. Wait. Oh, okay. Unfortunately, I didn't have time for the. Let's take a break, and then I will continue. I will just speed up. Okay, can we take a 5-minute break instead of 10? Now it's 2 o'clock. Oh, I mean 6 o'clock for you.
Okay, no problem.
Okay, all right. See you guys in 5 minutes. Sorry,
Okay.
Running late. All right.
Also, may I ask a question during the break? When you solve the SDP and then you remove the rank 1 constraint, but in the end you need to recover the voltage vector from probably higher rank matrix. How do you achieve this thing?
So if I understand your question, if you get a W.
Yeah, you get the W and you want to recover the matrix vector V.
That's right, that's right. So if W optimal is PSD n rank 1, then there's a unique decomposition. There will be a unique V vector, unique up to a rotation, so that this holds.
Yeah, but
and then you do it, essentially you do eigenvalue decomposition.
Yes, but for the other case, for when you mentioned that when this relaxation is not accepted, then how do you recover this thing?
Oh, if this is not RAM 1, is that the question?
Yeah, because you mentioned that just radio is rank 1, but for the other thing is not. The relaxation will not be set.
That's right. Then you cannot recover a voltage vector. So what you can do, for example, what people sometimes do is that you get let's say you get a RAM 2 solution W, then you can recover you can use, so there will be, excuse me, say V1 plus some A of V, or I guess it can be a right? Then you can say
that you would do a eigenvalue decomposition, just take the largest one. Okay.
That's right. And that vector, on the other hand, does not satisfy Kirchhoff law.
Yeah.
That's the problem, right? And therefore, if you get a non-RAM 1 solution, it's not very clear what the solution tells you. You cannot get a feasible point. What people have done, for example, empirically, is that they would take the eigenvector corresponding to the largest eigenvalue and use that as an initial point, voltage vector as the initial point, and then run some local algorithm, for example, Newton-Raphson. And typically that works very well. Yeah, but conceptually, what is that solution, a optimal W that is not RAM 1 tells us? It's not very clear.
Okay, thank you.
Okay, so let's continue. Sorry. All right, so I'll try to speed up a little bit. Okay, so we've seen, just to recap, we've seen that in OPF, for your different applications, you have OPF with different objective functions, maybe different set of constraints. So the constraints that we saw earlier really represents the simplest, the minimal set of constraints. For most applications, you will have additional constraints, operational constraints. But in all those cases, typically you will be able to write your OPF either for a single phase model or three-phase model as a non-convex QCQP. For those problems, you can have semi-definite realizations, and you can have semi-PSD, you could have SOCP, for example, or you do a quarter extension, which will be much simpler typically than your full SDP realization. Okay, so the last question we'll look at is, under what condition will exact realizations turn out to be exact. So empirically, very often for radio networks, at least, we get exact realizations. Even for mesh network, that's actually quite common. So hopefully we'll have time to look at that question towards the end. All right, so we're going to, there's some sufficient conditions. Those conditions, they will guarantee exact realization, but they're only sufficient. Okay, there's some literature and so on. And again, the nice recent survey by Dan Mosen and Ian Hisken contains a lot more preferences. So we say a realization is exact if an optimal solution of the original OPF can be recovered from every optimal solution of the realization. Okay? So whether it is every optimal solution or there's one optimal solution of the realization from which an optimal solution of the original OPF can be recovered. That difference is actually not that not that important for OPFs that we usually see. So let me ignore that small subtlety. So we're going to look at three sufficient conditions. The first two are for radio network. The third is also for radio network but three-phase. Right? And therefore, for example, if you think of the single-phase equivalent, then a three-phase radio network is actually a mesh network. Okay. So the first two conditions are for single-phase radio network. Okay? And the first condition uses the polar form of your powerful equation, so that we we saw the complex form before, but you could look at the polar form. And really, the condition gives you a bound, imposes a bound on the angle difference across each line. So the geometric insight, let me try to do it very quickly. So suppose you have just two bus network, and this is the series admittance, so assuming zero line charging admittance, and theta is the angle difference. So the variables are P1, P2, and theta. Okay, so the real power injection at each node, and then the theta. Ignore the reactive power, and also you fix the magnitude. So these are like a little bit like the condition assumptions in DC power flow, except that we are looking at non-linear power flow equations. So okay, so let's look at the what's going on in the realization and when will that be exact. So the power flow equation in polar form will take this form. So P1, P2 can be written in terms of the theta. So G and B are the parameters of the line. So look at this form, you can eliminate theta, right? And you get a quadratic equation relating P1 and P2. That's the ellipse. The ellipse looks something like this. And as your theta varies, you are tracing out the ellipse, right? When your theta is small, when theta is 0, then this is the point of your ellipse. If your theta is small, that is close to 0 on either side, then you're tracing your ellipse here. When your theta is large, then it corresponds to your P1, P2 on the upper part of your ellipse. So that's going to be important as we will see in the realization. So if you look at the feasible set, where X, which is P1, P2 theta, satisfy the power flow equations, that's a feasible set. Okay. And OPF is simply you want to minimize certain costs over the feasible set. And the cost will be something like this, right? So let's say is the generation cost that you want to minimize, then you look something like this. And the optimal point in this picture is going to be here, right? Now, this is non-convex because it's ellipse without the interior. So that's non-convex, right? A realization, basically, if your realization is such that you're minimizing the same cost but over the entire ellipse, you're going to get an optimal solution that lies on the ellipse and therefore is exact realization, right? This is the case when there's no operational constraint. And therefore, the only constraint is power flow equation. Then if you relax, the realization and the original feasible set have the same Pareto optimal. the Pareto front, and therefore the relaxation is exact. Now let's consider what happened when you impose operational constraints, right? So on the theta and also on the p's, P1, P2. Right? So this first, if we impose constraints on the theta, what happened? Well, as we mentioned earlier, then depending on your theta, if your theta underbar, upper bar is small, then you are going to allow feasible set to be the lower part of your ellipse. Otherwise, you could include the upper part, right? So that's the effect of imposing constraints on theta. When you impose constraints on the injections, then you are, so this is the upper bound, right? On P1, P2, then you're going to carve out basic sections of your ellipse on the lower half if you are looking at the upper bound. If you look at the lower bound, then it could be problematic if your lower bound is high, because then you can just pick out the upper part of your ellipse, and we'll see that that can be a problem when you do relaxation. So this is the effect if you impose individually constraints on theta and then constraints on P, okay? So OPF is this. You want your X to be in the intersection of those three constraints, the powerful equations, the theta constraint, and the injection constraint. The relaxation is you look at the convex Hall of the powerful equation and also the theta, right? And then you take the intersection with X3. So if your theta is small, then you're picking out the lower parts. And the relaxation will have the same Pareto front, and therefore relaxation will be exact. Whereas if your theta is large, you're picking out the upper part. And if your lower bound on the injection are high, then you could have this situation where the relaxation is the blue region, and the optimal solution is going to lie on this line, which is not feasible. It's not on the ellipse. And therefore, your relaxation will have a solution that is not feasible for your original problem. And therefore, the relaxation is not exact. So that's the intuition, okay? And therefore, the first sufficient condition is restrict theta. If you restrict theta so that you stay on the lower side, then things are fine, right? So that's your OPF. You have a condition on theta. It cannot be too large on either side of zero. And a small theta can correspond to line loss constraints, line flow constraints, stability constraints, and so on. And the rest are the powerful equations, okay, and also the injection constraints. Then the condition is that if your theta, let's say the upper and lower bound, lies between some numbers defined by the Rx ratio, okay, then the SOCB relaxation will be exact. Okay, so that's the first condition on the voltage angles. The second condition is also for radial single phase network and uses a complex form, the powerful equations that we saw before, and the condition will impose bounds on the injections. It looks something like this. Let's look at a general QCQP. Okay, it takes the form, you want to minimize this quadratic form, x star c of x, and this is complex, and just like what we saw before. Okay? We restrict to the set of QCQPs whose underlying graph is a tree. So what it means is the following. Given the QCQP, so QCQP is defined for us, defined by the matrices, the cost matrix and constraint matrix. There's also parameter BK, but we don't really care about BK for this condition. And therefore, the QCQP for us is defined by the set of matrices C and CK. Given C and CK, then we can define a graph, underlying graph, such that there's an edge between node I and J if either Cij is non-zero or Ckij is non-zero for any k, right? So if any of the matrices C and Ck has a non-zero entry of diagonal entry, ij's of diagonal entry that is non-zero, then there's an edge, right? And if the resulting graph is a tree, then and this is the class of QCQP that we care about, right? So we're looking at QCQP over tree. Then the condition for relaxation is exact relaxation is the following: is that if you look at every line ij, okay, if you have k conditions, then there will be k plus 1 complex numbers, one from Cij, which is the cost constraint, one from Ckij, which is those k constraints. So ignore the magnitude of these complex numbers. We only care about their phase. Then you can plot them on a circle. If there is a line through the origin that separates all these complex numbers, so if all the complex numbers lie on one side of the line, it could be on the line, then the relaxation is exact. The implication of OPF, if you work out the QCQP for your corresponding to your OPF, it means that if there's no line, so that both the real and reactive injections at both ends of that line are both lower and upper bounded, right? Finite, lower or upper bound, right? Then the condition is exact. Okay. Okay. Let me just quickly go through the third condition. So this is for three-phase radio network. Again, it's a radio network, but it's a three-phase, and therefore whose single-phase equivalent is actually a mesh network, right? So this seems to be the only sufficient condition that involve mesh network. That's general. Not, I mean, there are also other special cases for mesh network. Okay, so okay, so this is a nice result from my grad student Feng Yizhou, and also a visit student Yue Chen. Okay, so okay, we care about radio networks because distribution systems are all radio networks, and they are multi-phase, three-phase, right? So in the three-phase case, you get this this matrix that we saw before. Okay, so you can form, again, you can think of it as a single-phase equivalent. You can write down the OPF and all that. Okay, so critical bus. We say a bus J is critical cost bus if the cost function involve basically the injections at J, okay, for some phase at J, right? So if the cost function depends on injections on some injections of some phase at J, then this bus is a critical bus, okay? Or if you look at the injection limits, okay, so there's a real and reactive power injection, upper and lower bounds, so those 4 bounds. If all 4 bounds are finite, then that's a critical bus, okay? So that's what we call critical bus. The restriction is exact if no critical buses are adjacent. And also no bus is both a critical cost and also a critical constraint bus. Okay. So it's relatively simple conditions for a mesh network. It's pretty general mesh network. It's radio, but other than that, it's a 3-phase radio. Right? So the kind of networks that we care about. All right, let me stop here and start the second half of the lecture. Okay, so we'll talk about the disk flow model, and we'll probably skip some of the lean disk flows. Maybe some of you are familiar with this flow, that would be great. And then look at the SOCP relaxation, and then look at the 3-phase extension. Okay, so the original disk flow, SOCP, and then the 3-phase extension. Everything in the single-phase case, even the linearized version of the disk flow equations, has a corresponding 3-phase correspondence. Okay, so this is the these flow equations. So this is the power balance. Sj is small sj is the real and reactive power injection. Capital Sj is the line power, sending end line power from I to j, okay? Real and reactive, sending end. Lij is, you can think of Lij really as the current, sending end current from I to j, but magnitude squared. Okay, so now this is in complex notation, but really this represents two equations, one for the real power, one for the imaginary power, right? So this is just shorthand. So in these flow equations, all variables are real. Okay, this is Vi is voltage phasor magnitude square. Okay, and therefore this is a real number. Right? So Vi minus Vj is the magnitude square, and node I minus the voltage magnitude square and node J. This is the impedance, series impedance of line Ij. H is the complex conjugate times the complex number Sij, which is a sending end complex line power from I to J, right? And this is the magnitude of impedance square, and then this is the current, right? Again, the right-hand side is in complex notation, but it's just a shorthand. You can write everything in real, right? So all these are real equations. And then the last one is this, Vi Lij, which are this, equals, this is basically Pij squared plus Qij squared, real and reactive complex line power, okay? And therefore, the variables are real, right? M is the number of lines, N is the number of buses, okay? So, so this is the this flow equation. This is linear in the variables. Variable is X, right? All of this. The nodal injection, the line power, the voltage magnitude square, the current magnitude square, okay? And this is quadratic, and this is the non-convexity. This is the only non-convexity, okay? Okay, so this was the original this flow equation proposed by Baran and Wu in 1989 for radio network, single-phase radio network, okay? And this is the burst injection model that we saw before. Different equations, different variables. One is complex, one is real, right, and so on. But they are equivalent. We'll come back to this in some sense. So there's a linearized version of that. Let me skip that. The linearized version has a lot of interesting properties, but let me skip that. Okay, so this burst injection model is for general network, not just for radio, right? For network containing cycles. This flow model is really only for radio. So if you have a mesh network, what's wrong with this set of equations? So it doesn't describe the behavior of your mesh network unless you add additional constraints, and that's a cycle condition. Okay. If you have a radio network, then the cycle condition is vacuous, and therefore this flow model will be equivalent to the burst injection model when you have a single phase radio network. Otherwise, it's not, unless you add a cycle condition. So let me skip the cycle condition. It has the same interpretation, but it's expressed in terms of the variable X. Okay. Okay, let me skip that, skip the detail. And therefore, if you write down the full branch flow model, that is this flow equation plus the cycle condition, then indeed you can show that these two set of equations have the same, have their solution sets. There's a one-one correspondence between the solution sets of these two set of equations, right? One in complex, one consists of real equations. But there's a linear bijection between the solution sets of these two set of equations. So it is in this sense that we said these two models are equivalent. Okay, and therefore any problem that you can formulate in one model, you can, in theory, just go through the linear bijection and obtain in the other model. But some results are easier to formulate and prove in one than the other. So for example, SDP is simple and natural to formulate in the bus injection model, as we saw earlier. Is you can formulate that in bus injection model, go through the linear transformation and get a corresponding SDP in the branch flow model, but it's a mess. It's really difficult to see the structure. Similarly, there are some results, such as the one that we're going to see later on the exact realization, that's formulated and proved in branch flow model. That seems very difficult to formulate and prove in the bus injection model. And therefore, you should just use any one of the model that is more convenient for your applications. The second thing that we notice, we don't quite understand, but there's very strong empirical experience where the branch flow model seems to be much more numerically stable as we try to solve large cases. And also, branch flow model is really designed for radio network. If you have a radio network, then it has a very efficient back and forward sweep to compute powerful equations. And that's also useful in solving OPF as well. And the linearization, which I skipped, is much nicer for, let's say, than DC power flow. So DC power flow is really for transmission network. For distribution network, it's not suitable in many ways. And the linearized version of the DC flow equations is much nicer. And that's what we're trying to get to. Everything that we talk about in the single phase has a correspondence in the three-phase unbalanced network. Okay, so let's look at the single phase SOCP realization. So this is the branch flow model. This is this flow equation. You can add the cycle condition. And the OPF for general networks, say network that may contain cycles, you have minimizing a certain cost over the set of variables for your branch flow model. Everything's real, subject to operational constraints, and then you have these power flow equations that we saw in the previous slide. That's non-convex, right? The non-convexity, here. The non-convexity is the quadratic equality and also the cycle condition. Now, if you're a radio network, then this is vacuous. You can ignore that. It's automatically satisfied, and therefore you can ignore that. So in the realization, whether you have a mesh network or radio, what you do is that you ignore this. So you cross this, and then you change this to an inequality. That's a second order condition constraint. Okay? So that's a realization. And this is realization. You just get the inequality here and ignore the cycle condition. Okay, so this is SOCP realization. Okay, so you really enlarge your feasible set to be a second order cone. And it is exact for radio networks, single phase radio networks. If this is the condition that we saw earlier, because branch flow model and bus injection models are the same. So the conditions will be applicable to either model. The second condition that's formulated and proof in the branch flow model that is very difficult to formulate and prove in the bus injection model is essentially if the upper bounds on the voltages are not tight, then you have exact realization. So, okay, so we have 30 minutes or 25 minutes. Maybe we can look at that. So that's the flow chart that we've been talking about. So let me skip that. Okay, so a realization is exact if an optimal solution of the original OPF can be recovered from every optimal solution of the realization, right? So that's the same definition we saw before. So let me explain, let me at least just give you an intuition what happened, right? What the voltage upper bound. If the voltage upper bounds are not binding, then essentially you will have an exact SOCP relaxation for a radial single phase network. So here's the intuition. Let's say again, consider two bus case, right? Two buses, and the variables in the distro model will involve the think of this as the substation bus that provides the you can positive and negative, but think of that as it provides the power. This is the load that is given, right? So this is the supply, this is the load. The voltage at the substation bus V0 is given, fixed. So this is the voltage magnitude square. And the voltage at the low bus is a variable. And then the current magnitude square on that line is a variable. So the variables are the substation injection, the line current magnitude square, the low voltage, right? So you write down the equation, powerful equations. So these are the variables. You write down the equations. Yeah, so these are the equations basically. So the bottom line is the feasible set consists of just 2 points here and here, which is the intersection of a bow and a line, right? The intersection of these two objects defines the feasible set. That's the consequence of your powerful equations. And therefore, it's not convex, it's two isolated points. A SOCP relaxation will expand the feasible set to be the line segment that contains the 2 points. So that's a convex. Right? So that's the first thing. The second thing is that these two feasible points, one corresponds to low voltage, low voltage, and high load voltage, right? High V1 and low V1. And the third point is that if your cost function is increasing in the current, let's say if your cost is minimizing the line loss, then it's increasing the current magnitude square, right? Then the optimal solution for your original OPF, you have to choose one of those 2 points. Then the optimal solution is going to be the high voltage point because that has a lower current L. Now, if there's no other constraint, then the relaxation corresponds to minimizing the cost, which is increasing in L, over the entire line segment. And therefore, the point C is still going to be the optimal point for your relaxation. And that's why your relaxation will be exact. So again, this is the case when the feasible set is defined only by the powerful equations, but there's no other constraints. What happens if you impose voltage constraint upper lower bound? What happens is this. SOCP and largest is a line, is exact if the cost is increasing in L and that there's no voltage bound. Okay, so what happens if you impose voltage constraint? Well, if you impose voltage constraint, the lower bound is going to cut off from the top. And therefore, if you impose the lower bound, when you increase the lower bound first on the voltage, it's going to cut off from the top, but the C will remain. If you impose upper bound on the voltage, it's going to go in the opposite direction. As the upper bound decreases, it's going to cut off in this going up. And therefore, if your voltage upper bound is too tight, you may come to the situation where you cut off the point C. C is no longer your feasible set. And therefore, when you do your relaxation, then this is your feasible set. This is going to be your optimal point that is not feasible. And that's why your SOCP relaxation is not exact. Whereas if your voltage upper bound is not tight, then you are in this situation. The point C is still in your feasible set, and therefore the relaxation will be exact. So that's what happened. So let me skip the, basically, the intuition for the two-bus network can be proved formally for general network, for general radio single-phase network, right? But the proof is much more elaborate than, of course, than in the two-bus case. Okay, so let me describe the three-phase extension. So what we have for a single phase, we have a this flow model. You can amend that with cycle condition. You have a linearized version, which I skip. You can show that it's equivalent to the bus injection model. You can have SOCP relaxation, and you have sufficient conditions for exact relaxation. All of these except the sufficient condition for exact relaxation has a three-phase correspondence. That's the bottom line. So what it looks like is the following. So this is the single-phase model that we saw before. And this is the relaxation, right? You just ignore the cycle condition, you change equality into inequality, you get a second order cone. Now in the three-phase case, if we have a three-phase Y connection, the devices, the loads, then the key idea, this is my former student Lingwen Gan's idea, this is really a nice idea, is define the variables to be the outer product. So small vi is a 3x3 matrix, which is an outer product. Think of that as the outer product of your voltage phasor vi. Similarly, the current Lij, this is going to be a variable, small Lij, right? That is the outer product of your current phasor, right? So the current phasor and the voltage phasors are not variables in that three-phase model that we're going to see. But the intuition for the variables small Lij and small vi is this relationship, right? So that's the intuition, and that's the clever idea. And then similarly, Sij is the 3x3 matrix. And this is the condition. So this is part of your model, is that this matrix is PSD and RAM1, okay? Now, again, these are just some matrices VI, right? So they are not this, there's no voltage phasor as a variable, right? So small VIs are just 3x3 matrices, but I require this set of matrices to satisfy this PSD and RAM1 condition. Then the other two set of equations will be very similar to the single phase case, right? So this is the, this is like this. This really comes from the Ohm's law. It's really the Ohm's law, take the magnitude square and manipulate a little bit, right? So that's where it comes from. So these are scalars in the single phase case. In the three phase case, these will be 3x3 matrices. Okay. Similarly this. So these are scalars. In the three phase case, those will be the diagonal entries of your 3x3 matrices. Okay, so it looks like this. Okay, so this is the Vi minus Vj thing, right? So these are all 3x3 matrices. So these are Hermitian transpose. H corresponds to Hermitian transpose. So these are 3x3 matrix, 3x3 matrix, 3x3 matrix. Right? So this equation has to hold for the set of matrices, 3x3 matrices that defines the variables. Okay? And this is the power balance. And we only look at the diagonal entries of these 3x3 matrices. And this is the injection. This is a three-dimensional vector. Okay? And therefore, this is a three-dimensional vector equation. Now, what it means is that this equation, the power balance alone, impose constraint only on the diagonal entries of these 3x3 matrices. The off-diagonal entries are not constrained by the power balance equations. They are constrained by the other equations. in particular, very importantly, by this equation, which is non-convex. Okay, so this is the model. So this is the model Lin-Wen-Gan defined. It's a very clever model. It corresponds, it reduces to, so these are 6x6 matrices, 3x3 matrices, and so on. It reduces to the original disk flow equations if it is single phase. So then everything just becomes scalar. But the right generalization to three phase is actually this set of equations. It has all the nice properties, all the right properties. Okay, so it's equivalent disk flow if it is single phase. Okay, and therefore OPF in three phase, if your Y configure lows is simply operational constraints, and then the set of equations that Lin-Wen-Gan proposed to be the powerful equations for three-phase network, radio network. This is the only non-convex constraint. These are all linear in the matrices, matrix variables, and this is convex in the matrix variables, and therefore the relaxation corresponds to just ignore them, ignore the RAM constraint. Okay. So these are 6x6 semi-definite constraints. What is nice is that these constraints are scalable in the sense that it doesn't depend on the size of the network. They're all, the size of the network will give you more of these constraints, but each constraint is small. Okay, so you can show that in the three-phase case, the two models are also the same in the sense that the solution set or the feasible sets have a one correspondence between them. And therefore, one is exactly one model, even only if it is exactly the other model. So this simply shows that the branch flow model for large network is much more stable numerically, just empirical observation. Okay, so in the last 10 minutes, let me try to go to the last topic. Okay, let me start with a summary of what I want to say in the next 10 minutes, right? And then we'll backfill the details. So we saw OPF is non-convex, and in fact, it can be shown to be NP-hard. And therefore, it is hard in theory. In practice, it seems easy in the sense that if you do semi-definite relaxation, it often is exact, even when the sufficient conditions are not satisfied. If you just run, say, Newton-Raphson, interior point algorithm, some local algorithm, very often you get global optimal. Now you can check whether the solution you get is globally optimal by solving semi-definite relaxations, right? If you solve the semi-definite relaxation, you get the same cost. Then what you get is globally optimal. The question is why? Well, we don't completely understand, but here's some analytical properties that at least help explain some of the empirical observation. Okay, so we know that there's some sufficient conditions that will guarantee exact relaxation. They are sufficient but not necessary, but at least there's some conditions we understand that will guarantee relaxation is exact. I will present some results by Feng-Li Zhou recently that shows sufficient or necessary conditions for a non-convex problem to have both exact relaxation and also no spurious local optimal. Okay, and therefore every local algorithm will give you a global solution. Okay, so that's the summary. Okay, let's fill in the details of this. So we saw this before. OPF is non-convex. It has also been proved to be NP-hard. So here's just one example of the proof that reduces the subset sum problem to a AC feasibility problem for a radio network. Right? So the details are in the reference, but it's NP-hard, OPF in general. So here's an empirical experience. Many people have similar experience, and this is from some of our early, many years ago, early experience, where if you simulate HV test systems, Southern California Edison, local utility company, real networks, and so on, basically the SOCP is exact. These are radio networks. For mesh networks, STP is exact very often, right? Even when sufficient conditions are not satisfied. So these are early results. And if you, in these cases where the realizations were not exact, right? So these are way back 2013. Then we can check, we can run local algorithms and obtain global solutions. So these are less than 0.5% of from the lower bound, which is strict lower bound when it's not exact, right? And then there's a recent 2020 really extensive set of simulations that look at basically almost all the major test systems and run semi-definite realizations. They're very often exact. And if you add additional enhancements, such as adding some valid cuts and so on, you can close almost all optimality gaps. So this is after you apply some techniques developed in the paper, then almost all cases have optimality gaps less than 1%. Almost all cases have less than 1% optimality gap. So it suggests the local algorithm will give you a global solution, right? So that's okay. So indeed, okay, now let's try to look at try to understand this phenomenon analytically, right? Not fully yet, but it offers some explanation. So we already saw there are sufficient conditions that will guarantee exact realization. So that part we have some understanding. We want to look at the case why for OPF that we have both exact realization and global optimal. So for exact realizations, we know some sufficient conditions. For the second property, no spurious local optimal, is widely observed empirically, but until Feng Zhou's result, CDC last year, there wasn't, as far as we know, we couldn't find any results that try to explain this analytically. So here's Feng Yu's result. So it's very general. Let me see how. Oh, okay. So we have a few minutes. It's very general. Suppose you have a non-convex optimization problem. So you want to minimize f of x in a feasible set capital X or script X. The assumption is that the objective function is nice, it's continuous in convex. The feasible set is non-convex. We assume it's compact, but it's non-convex, right? So that's the problem. So this is the feasible set, the non-convex feasible set, and the realization is simply to minimize the same function over a convex superset X hat, right? So that's the green area. Okay? And we assume the superset X hat is also compact, is convex, it contains the original feasible set. So the setup is very simple, very general. And we say that the realization is exact if there exists a optimal solution of the realization. So it's not every optimal solution, but if there is an optimal solution of the realization that is optimal for the original problem. Okay, so that's the definition of exactness in Feng Yu's result here. So his result will give you some conditions that will be sufficient or necessary for both. For both the realization is exact and also no spurious local optimal. Okay, so here's just to state the result. Here's a set of the results. The first concept is the path. For every point X that is not feasible, So capital X is the blue set is the non-convex feasible set. The brown X hat set is the relaxation, right? So for every point that is not feasible, which is X, a path is a continuous function, say mapping 0 to 1, that starts from the point X that is not feasible and end up in a point HX1 that is in the feasible set, right? So if you give me a infeasible set, I can find a path to get back to the feasible set. That's the path, H of X, right? One for each X, okay? So 2 will be exact, the relaxation will be exact. If for every point that is not feasible, there is a path such that the cost function is non-increasing when you travel from X at H of 0 to the destination X of 1, right? So the cost will, think of the cost as decreasing, right? It's not decreasing. And at the end point, it has to be strictly smaller. So when you go from the infeasible point X to inside the set, at the end, your cost will be strictly lower. So that's the requirement. And en route, it cannot increase, okay? So that's if this condition is satisfied, if and only if the relaxation will be exact. So that's okay. The second important concept really is the Lyapunov-like function. So it looks something like this, right? So it's a V of X that maps from the relaxed feasible set X hat, okay, to R plus. So that is strictly positive at a point that is infeasible. It is 0 on the feasible set, right? So it's like this MATLAB symbol, right? Okay, so I guess everyone is familiar with the standard Lyapunov function, right? So we have a dynamical system, y dot equals f of y, and we want to show that it's globally asymptotically optimal, so yt will converge to some y star. The way we do it is we try to find a Lyapunov function so that v of y is strictly positive unless it is at the optimal, at the y star, right? The equilibrium point, for example. And the v dot, so the v decreases along the trajectory of yt. So that's the standard setup. In Fournier's case, the trajectory is not specified. Right? We have to find this h of x, right? Whereas here in dynamical system, we specify the trajectory, right? Given f, in theory, we know the trajectory. The goal is to enter the feasible set, starting from an infeasible set X and end up with inside the feasible set, okay? And the Lyapunov-like function is such that this is what we have. We define a Lyapunov function. And then the second condition corresponding to this is going to be a condition for in Fournier's result, which is that the Lyapunov function V is non-increasing. Think of it as decreasing along the trajectory, right? Like the standard case, like the standard Lyapunov function case. So that's the comparison between the two. And also we need the cost to also be non-increasing along y of t, okay? And at the end is strictly better. Okay. Okay, so the condition is this. There is a path for every infeasible point x, right? H of x. And also a Lyapunov-like function, okay, such that condition C1 is that both the cos f and the Lyapunov function is non-increasing. So it's like decreasing along the trajectory. And at the end point, the cos f is strictly less than the initial cost at the infeasible point. Okay, so that's like the condition we saw before. The second condition is that it's just some regularity condition or some smoothness condition that the family of all the paths, one for every single infeasible point, this huge family of path need to be uniformly bounded and equicontinuous, right? It's uniform across, not only across every point on the path, but also across every path, okay? So if C1, C2, so C1, C2 are necessary. So meaning that if all local optimal of one are globally optimal, and if relaxation is exact, then C1, C2 must hold. There must exist a set of paths, one for each infeasible point, and there must exist a Lyapunov function that will have these properties. They are not sufficient. And the problem is that, okay. Let me skip the problem. Let me just give you the sufficient condition. So the third condition is that the cost function is not only decreasing, but also it decreases at some minimal rate, sort of. Right? So it's almost like a Lipschitz condition. Right? So it basically requires the cost function to decrease sufficiently, okay, to eliminate this what Feng calls pseudo local optimal. See, some things like that. That locally it looks like a local optimal, but it's but you can actually still further decrease if you go down this direction. So C3 is to eliminate this possibility. The C1, C2 is to eliminate local, sort of a more normal local optimal, what Feng call genuine local optimal. All these are local optimals, okay? But it differentiates between two types of or three types of local optimal. Then what he shows is that this C1, C2, C3 will be sufficient for no spurious optimal, local optimal, and also exact relaxation. Okay, so this is just pictorial, visualize the conditions. Okay, so let me skip that. The last part is just to say, okay, you can apply this to OPF, the branch flow models and so on, and indeed it works. Maybe I will close with the last comment, which is, okay. So unlike some of the results, let's say in matrix completion results, where people look at very nice structures that will guarantee no spurious local optimal. So in those results, the problem typically is that the non-convexity are in the objective functions. And therefore, the proof often involve evaluating the curvature of objective functions and so on. So here in OPF, the objective function for us typically are nice and convex. The problem is in the feasible set. That's non-convex. And therefore, Feng's technique is applicable in that situation. Okay, thank you very much. I will close here. Sorry for running a little bit tight. Any questions? Or we can just, time's up, sorry.
Yeah, I guess if there are a couple of questions, we can extend the session by a few minutes. So if anyone has a question, just please raise your voice or write a comment in the chat and I can read it out.
So maybe I ask a simple question. Thanks a lot, Professor Lau. My simple question is about so in the power system, normally the people distinguish the AC power flow and the DC power flow. But in principle, there are several, I think, forms about the DC power flow. In principle, most all of them are just how to say linearized or convex, affine form. So I'm curious about all this DC OPF form. What's the relation between this DC OPF form, power flow form with respect to this relaxation? Is there any connection between them?
It's not very clear. And the reason is because in relaxation, at least you get a bound, right? Because right. In DC power flow is an approximation. It's not very clear the relationship between the approximation, DC approximation, and the original problem.
I see.
And therefore, it's not
Okay.
very clear what the relationship will be between the DC power flow approximation and a semi-definite relaxation.
I see. I see. But sometimes they simply just linearize the AC power flow equation, then they call it just the DC.
That's right. So if you do linearization, typically depending on if you just, let's say, linearize Taylor expansion around some things, then in general, if it's non-convex, it's not very clear how that relates to the original problem. And this is where I think the this flow model, if you have a radio network, has a huge advantage because the linear model in that setting actually has a very nice, simple relationship between with the original problem. So for example, if you solve the, let's say the voltage from your linearized model, and you solve the voltage for your non-linearized model, then the linearized model always upper bounds the nonlinear voltage, for example. And similarly for the line flows and so on. There's a nice relation, very simple relationship where the linearized solution bounds the nonlinear solution. So you don't have that typically in the linearized model for in the bus injection model.
I see. Okay, so I have the last question. So, so I worked a bit about this distributed AC power OPF problem by using some second order distributed optimization. Well, yes, theoretically we can only get a local minimizer since it's a non-convex problem. So actually, I was thinking about if we use since the relaxation is a global optimizer as the problem is convex. So is it possible to use this relaxed solution to judge so my non-convex local minimizer is good or not? So what I think this is for generic mesh the grid. It's not about for the radio network.
Right. So if I understand your question correctly, I'm not sure, but if I understand your question correctly, then a relaxation always gives you a lower bound because conceptually, right, and therefore you solve relaxation, and then it may not be exact. If it's exact, then you get a global solution. That's the end of that. It may not be exact, but you can run local algorithm to get a feasible point, and then you can compare the cost of your feasible point with the cost of the relaxation. If that gap is small, then it means your local solution is very good.
I see. Okay. I see.
If the gap is huge, then you can't. Your local solution can still be very good. It's just the relaxation is very poor.
Yes. I see. Since
so
I tried.
Go ahead.
Sorry. Yeah, since I just want to see, I try to test my algorithm so with a different initial point. Since I in my opinion, even for a 5-bus benchmark, you might have several local minimizer. So I just simply write them generate 300 initial point to run my algorithm. I don't know why I always get a single local minimizer. It's quite, it's a little bit weird. So I was a bit, curious about it possible to show even for this kind of a very small benchmark only have single local minimizer, which is global.
Is possible, hard to say. What we found sometimes is that the contour tends to be very flat near the optimal. I don't know whether that's your situation or not. That's one thing that we've found often. And the effect of that is that you can you can have different runs, initial point. You may get to a different optimal solution, but their costs are all very, very, very close. Now, of course, it can also be U condition, and therefore it's very, in that case, that it's hard to interpret what those numbers mean.
I see.
So we don't really understand about what the contour looks like.
I see. Thanks a lot. Actually, I mean, so my question is basically on my experience. I always use this, how to say, like, SQP or interior point method, which can only applicable for finding the local minimizer, but not for the global minimizer. That's why I'm just curious how to evaluate my result. But I think, yeah, your answer is very, very helpful. Yeah, I think I got the proper answer. Thanks a lot.
Sure.
Maybe I have one question. Thanks, Professor Lowe, for a very nice talk. Yeah, I have a question more on application point of view. Like, I have often seen that when you implement OPF for control purposes, like MPC and stuff, people often go towards linearized power flow, like first order Taylor approximation, rather using AC power flow, because it becomes heavy if you do an MPC, considering all the different time steps. So I was just wondering, like theoretical point of view, all this research is very interesting and gives you nice insight. But yeah, are there like practical applications or implementations of this ACOPF for control purposes, for example? Yeah.
So, right. So there are two things. One is ACOPF, one is relaxation.
Yeah.
So certainly for the first one, the ACOPF, they are being used for some applications, and there's a strong effort by, for example, by many parties, but for example, Opt&E in the US, they try to really develop solution methods that can solve large-scale ACOPF problems. And if that can be done reliably, then there will be a strong incentive to move the industry to solving ACOPF rather than currently solving DCOPF mostly in the market. Now, where that effort is that some of you might know that there's this Opt&E Go competition. That's one of such efforts to really try to do that. And in that competition, indeed, people have developed various kinds of techniques to scale to very large networks that are really at a practical size. Now, the endeavor is very promising. As far as I know, none of those use semi-definite relaxation. This is not very scalable. But they are various techniques that people have developed that's really tailored for, in challenge one is the SCOPF. That seems to be very successful for solving the challenge one SCOPF problem. Now, if indeed that effort continues and it becomes successful and the industry does move to solving ACOPF rather than DC, the expectation is that it can save billions of dollars every year. So billions of dollars, is that a huge amount? Since that's more amount, hard to say nowadays. But is in a sense free money, right? So if you just improve your software, you save, it's worthwhile to do. And therefore, there is a strong incentive to really try to solve it. Right now, I think is really the inability to solve large-scale ACOPF reliably and also quickly. That is the bottleneck, rather than lack of interest.
Yeah, I mean, what I have seen is that ACOPF and its relaxations are mostly used like widely in even in planning problems, but not in control problems. People avoid to use it probably because you cannot guarantee the feasibility. Maybe if you do the relaxation and your network state might reach to one condition which you cannot recover from or something like that. Rather, people go for some gradient descent methods which just go into the feasible set and then you do the control. For example, first order Taylor approximation. Yeah. Okay. Thank you. That was my question.
Sure. Okay. Kind of late.
Yeah, all right. I think we can start slowly closing the talk. So, and finally let you go to sleep. So thanks for being with us today again. And